Greetings everyone, I am Hechenberger, and today I am presenting our paper Online Computation of Euclidean Shortest Paths in Two Dimensions that is being released in the Proceedings of the ICAPS 2020 online conference. This paper is on the Euclidean shortest path problem, where we take as input a start point, a target point, and a set of polygonal obstacles. And it will find the shortest path from the start to the target that does not intersect any of the obstacles. Current method of solving this problem is by means of the visibility graph. It will generate a graph from the input, where the vertices are the corner points of the obstacles, and the edges are the pairs of corner points that are visible to one another. In other words, doesn't have any obstacles between them. A visibility graph has up to v squared edges in complexity, resulting in a large memory overhead for a large environment. Sparse visibility graph is a variation on the normal visibility graph, where it will only keep edges that can be on the shortest path. This greatly reduces the number of edges that we can see here. It is a lot less dense. The navigation method is another way of solving this problem. It essentially inverts. By taking the non-traversable obstacles, it will instead produce traversable faces that you will navigate through. It has a state-of-the-art solver known as polyanya, and this requires less memory than the visibility graph and is also easier to construct. Well, it's faster to construct. And although, like a visibility graph, it is not solving the problem of polygonal obstacles directly. So we introduce Rayscan, an online method for solving the Euclidean shortest path. This works as an on-the-fly partial visibility graph that uses A-star search. So what this means is it will generate the edges of the expanding node as you go. Therefore, we do not need to have an entire visibility graph. So, we will show by example with a start and target point. From S, we start by shooting a ray towards target point V. This ray shooting will intersect any polygon obstacles that are in the way, and we'll be able to tell where it intersects it. However, so in this case, target is a visible point, so it can be added as a successor. A direct line of sight from S to T is the simplest case that Rayscan doesn't have any difficulties with. On a more complicated case is when this target is blocked, so in this case we've got a polygon in the way. So, we have an obstacle that is blocking at this point here, and we need to navigate around this obstacle. We introduce the concept of scanning, where we can scan counterclockwise from this point to find A, and clockwise from this point to find B. Both of these points are called turning points, but they're relevant because you can bend around the obstacle in this way. This can be, which means it could be on the shortest path. So, we now look at how you add the successors. We can shoot another ray to A, and we find that A doesn't have any obstacles in the way, meaning it is visible, and as such, we add it to the queue. Turning point B, on the other hand, is blocked by this square right here. So, the idea is that the ray directs the search. We want to find a way of reaching point B because point B may be able to reach the target point. So, to do this, with the since B is blocked, we recurse. Like we did with ST, we scan counterclockwise to find C and clockwise to find D. And as you can see, both of these cases, they are visible, thus will be added as successors. Since it's a recursion algorithm, it is possible that you may get infinite recursion unless you have an end condition. The end condition here is the angled sectors. So, this angled sector restricts where the scan can go. When you're scanning along a polygon edge, if you ever leave this angled sector, the scan ends. So with this one we scanned S to T, found B, and from S to B we scanned to find C. This green angled sector is the sector for where we find C, and we can tell from B to C here that from this point along here, we never left the angled sector. Therefore, this is a valid scan and we can proceed as normal. Once we found the C, we can shoot a ray beyond C to continue finding other successors that we may need to find. So in this case, you split the angled sector along the ray line into two, the green and the blue. And And we'll discard the blue because we only need to scan counterclockwise in this case. So from the S to C line here, we can scan counterclockwise along this edge, but we notice that we leave the angled sector on our way to finding turning point A. Therefore, the scan will end and we do not proceed any further. The end condition has been met. Now we go into the next expansion. We found the successes for S. Now we want to pop A from the priority queue as it's the best looking point. So this A has a special angled sector known as the projection field, and this is relevant as all successes need to fall inside this field in order to be able to bend around the polygon. This greatly reduces the number of successes we need to find. So when expanding A, the target point is within this projection field, which means we can shoot a ray to T, and in this case the target is visible, therefore it gets added. And as a result, since we found the target successor to A, we can end the scan there. Since if we use a Euclidean heuristic for the A-star search, then the search will end here, and we found our shortest path. Now, let's have a look at this here. This is all the successes we found. If we notice from S, we got these squares that are visible from S, but they weren't added as successes, whereas in a visibility graph, they would. Just because we didn't add them as successes doesn't mean we won't find the shortest path. If target was behind one of these squares, the ray would have hit them, resulting in edges being found. Therefore, our method is not going to find every edge that a sparse visibility graph will find, but it will still maintain optimality. This works because of the concept of the ray directs the search. If the ray didn't hit a polygon, then you did not need to navigate around that polygon. Now, taking this example to a larger level, we'll compare against the visibility graphs. So this diagram shows Rayscan and all its search successes. So we've got the red line is the shortest path, and the blue lines are the successes that were found during the search. If we compare it to the sparse visibility graph, these blue lines show the sparse visibility graph. The red lines are edges that were expanded during the A-star search. As we can see, most of the edges were found. So we compare against Rayscan, it is a lot less to the sparse. Now, if you were to take the concept of the projection field and apply it to a node you're successing, if you only add the successes of the sparse visibility graph within that projection field, you will greatly reduce the number of edges expanded. This was referred to as toward A star by the creators of the sparse visibility graph. And this is relevant because when you have a sparse visibility graph using toward A star, the successes are fairly similar to what Rayscan is. It's just Rayscan doesn't need the whole graph to work. Now, if we look at some of the practical results, we did tests using the Moving AI Labs pathfinding benchmarks. This is on the StarCraft Aurora map, and we compare Rayscan against its biggest competitor, Polyanya. So there's two different ray scans that we use. The first one is the squares representing the Bressingham ray shooting, which is a method of being able to handle the ray shooting of finding the closest obstacle in the way. And the triangles is the Oracle ray shooter, where we discard the runtime for the ray shooting. This gives us a baseline of how fast the algorithm can get. And as you can see, the ray shootings make up more than half of the time is spent in the time to shoot every ray. To recap, Rayscan works directly on the environment. It is well suited to a single or dynamically changing maps, and its performance is heavily dependent on the ray shooter you are using. So, I'd like to thank you all for coming to listen to this presentation, and I hope you enjoy the rest of the conference.